quantum entanglement.
Mm-hmm.
You probably heard it called spooky action at a distance. It's this really strange connection where particles get linked.
Intimately linked.
Exactly. And their properties stay correlated instantly no matter how far apart they fly off in the universe. It's wild.
It really is.
But here's where it gets, well, even more interesting for our deep dive today. Not all entanglement is really the same.
Not at all.
It seems the type of particle involved really changes how this entanglement works and, crucially, what we can maybe do with it.
Yeah, the applications.
So our mission here is to unpack this diversity. We'll look at how entanglement shows up differently for, say, photons versus electrons or atoms, even quarks.
Right.
And why these differences are so important for, the quantum technologies people are trying to build. We're basing this on some great material called particle-specific quantum entanglement, nature, creation, and applications.
And what's really key here, I think, is that the basic properties of the particles themselves, things like, does it have mass? Does it have charge? What's its spin? These aren't just details.
Okay.
They fundamentally dictate how you can create the entanglement, how you can mess with it, control it, and ultimately what you can use it for. It's a really deep connection.
Right, between the particle's identity and its quantum behavior.
Exactly.
Okay, let's unpack that. So if entanglement links properties, what exactly is getting linked? Let's start with photons. What's entangled there?
Okay, photons, they're massless bosons, right? Like particles of light. For them, the property we usually talk about entangling is polarization.
Polarization, okay.
Yeah.
Like the orientation.
Yeah, basically how they're oriented. So imagine you've got an entangled pair. If you measure one and find it's, say, vertically polarized, its partner instantly is found to be horizontally polarized, or vice versa, depending on the entangled state you create.
Instantly, no matter the distance. That's the spooky part.
That's the spooky part. And you can also entangle their momentum or energy, but polarization is, well, it's a very common one to work with.
Okay, so for photons, it's orientation. Very visual. What about electrons? Different beasts, right? They have mass, charge.
Right. Electrons are fermions. They're matter particles. And for them, entanglement typically involves something called spin.
Spin. Not like actual spinning, but an intrinsic quantum property.
Exactly. Intrinsic angular momentum. So an entangled pair of electrons can be in this quantum state, this superposition, where their spins are perfectly anti-correlated. If you measure one and find its spin is, let's say, up,
the other one has to be down.
Guaranteed. Instantly. And because they're charged, you can also entangle how they're moving, their motional states. But spin is really the classic electron entanglement property.
That's fascinating how specific it is. Spin for electrons. Polarization often for photons. Okay, so we've covered these sort of fundamental particles. What if we go bigger, like atoms or ions? They're more complex systems. Does that give us more options for entanglement?
Oh, absolutely. Yeah, much more complex. So you get a wider range of properties you can potentially entangle.
Like what?
Well, you could entangle the internal electronic energy levels of two atoms. So maybe one atom is in its ground state, the lowest energy state. And its entangled partner is in an excited state, but they're linked together in that state.
Okay, interesting.
Or for ions trapped in, electromagnetic fields,
Trapped ion,
you can entangle their motional states, basically how they're vibrating or oscillating within that trap.
So their physical movement gets linked.
Yeah, their collective motion. And what's really neat is you can even create hybrid entanglement.
Hybrid?
Yeah, like entangle an internal state of an ion with the polarization of a photon it emits or absorbs.
Wow, okay, so you can mix and match particle types.
You can really start combining these things. It shows how versatile these larger quantum systems can be.
And it goes even deeper, doesn't it? I mean, inside protons and neutrons. We're talking quarks and gluons there.
Yeah.
Is there entanglement happening inside?
Oh, absolutely. Inside particles like protons and neutrons, hadrons, the quarks and gluons that make them up are, well, they're constantly entangled.
Constantly, so we don't even have to create it.
Nope. It's just there.
Yeah.
It's a consequence of the strong nuclear force, the force that binds them together.
So what's entangled then? Their spin again?
Their spin, yes, but also something called color charge.
Color charge?
Yeah.
That's the strong force equivalent of electric charge, right?
Exactly. It's a property specific to quarks and gluons, and their colors and spins have to be entangled in such a way that they always combine correctly to give the overall properties of the proton or neutron.
So it's like a fundamental built-in entanglement.
It is. It's not something we engineer in the lab for, say, a quantum computer in the same way. It's more about understanding the fundamental structure of matter.
Which raises a big question then. If it's different for all these particles, how do scientists actually make and control these connections when they do need to engineer them, like for photons or electrons?
Right, the how-to and the techniques are, as you'd expect, really tailored to the particle.
Makes sense.
For photons, the workhorse method for creating entangled pairs is a process called spontaneous parametric down conversion, SPDC.
XPDC. Okay.
It sounds complicated, but the basic idea is you shoot a high-energy laser beam through a special kind of crystal, a nonlinear crystal,
Uh-huh.
and there's a chance, a small probability, that a single high-energy photon from the laser gets split inside the crystal into a pair of lower-energy photons that come out entangled, usually entangled in polarization or momentum.
So you need the right laser and the right crystal? Yeah. Sounds precise.
It's very precise engineering, yeah.
Okay, so that's photons. What about electrons? You said they're delicate, sensitive to noise because of their charge. How do you entangle them?
Yeah, entangling electrons is definitely trickier in some ways. One common approach uses something called quantum dots.
Quantum dots. Tiny semiconductor crystals.
Exactly. Nanoscale crystals that act like artificial atoms, basically trapping individual electrons. Okay.
Then you use really carefully controlled electric and magnetic fields to nudge these trapped electrons, make them interact, and couple their spins together into an entangled state.
So you isolate them in these dots and then manipulate them very carefully with fields.
Pretty much. It gives you that control you need, away from environmental interference as much as possible.
And for the bigger guys, atoms and ions. You mentioned lasers again, but used differently.
Right. Lasers are still key tools in atomic physics, but yeah, used in different ways. For trapped ions, for instance, you use precisely tuned laser pulses to manipulate their internal energy states, like we talked about. But you can also use lasers to cool them way down and control their motion. And then you can link their internal states through their shared motion in the trap.
Ah, so the vibration, the motion acts like a connection between them.
Exactly. That collective motion can act as a kind of quantum bus.
A quantum bus, like a data bus in a computer.
Sort of, yeah.
Yeah.
It's a way to mediate entanglement between ions that might not be directly interacting otherwise. Clever. And neutral atoms. No charge, so you can't trap them with electric fields as easily.
Right. For neutral atoms, a common technique is to hold them in what's called an optical lattice.
Optical lattice, like an egg carton made of light.
That's a great analogy. It's a grid of tiny light traps formed by interfering laser beams. And once they're held in this lattice, you can use other lasers to make nearby atoms interact in a controlled way, maybe induce controlled collisions to entangle them.
Okay, so lots of different, very specific techniques depending on the particle.
Highly specific, yeah.
Now, this isn't just, fun physics experiments. You mentioned applications.
Yeah.
These differences between particles must really matter for the kinds of quantum technologies people are trying to build.
Oh, absolutely. Profoundly. The choice of which particle system to use is often driven entirely by the specific job you want the quantum technology to do.
Right. You pick the best tool for the task.
Exactly.
So connecting this to that bigger picture,
Yeah.
where do photons really stand out? What's their killer app in quantum tech?
Photons are, well, they're basically the champions for transmitting quantum information.
Transmitting, okay, sending it places.
Yes. Think of them as the perfect quantum messengers. They travel at the speed of light, obviously, and crucially, they interact very weakly with their environment.
Which means they don't lose their quantumness easily. Less decoherence.
Precisely. Decoherence is the enemy of quantum tech, and photons are quite robust against it over long distances. So they can carry entangled states through optical fibers or even through the air or space without easily getting messed up. This makes them absolutely ideal for things like quantum cryptography, QKD, for super secure communication.
Secure communication makes sense.
And also for building the backbone of a future quantum internet. You need to send quantum states between quantum computers or sensors. Photons are the way to do that.
Okay, so photons rule for communication. What about the computers themselves, the actual quantum processing?
For quantum computing, the requirements are a bit different. Their particles like trapped ions and electrons, especially electrons in those quantum dots we mentioned, are really strong contenders.
Why them for computing?
Well, remember how electrons interact strongly because of their charge? And ions, too.
Yeah, which made them kind of tricky to entangle sometimes.
Right, but that strong interaction is also exactly what you need to make qubits interact and perform computations. You need them to talk to each other reliably to create the complex, multi-qubit entangled states that quantum algorithms rely on.
So their interaction strength is a double-edged sword. Harder to isolate, but better for processing.
Exactly. And systems like trapped ions, you can hold them very stably for long times and manipulate them with lasers with incredibly high precision, high fidelity.
Fidelity meaning you do the operation you intended to do.
Yes, very accurately. So for building the processors, these systems offer advantages. The choice between, say, ions or quantum dots often comes down to trade-offs.
Trade-offs like what?
Well, maybe speed versus stability, or how easy it is to scale the system up to many, many qubits. It's not like one is definitively better yet. Different approaches have different strengths and weaknesses for computation.
Okay, that makes a lot of sense. It's not one size fits all.
Definitely not.
So thinking about all this, for you, the listener, it really seems that from the way a photon is polarized, just fleetingly, to the really deep down fundamental links between quarks inside a proton, their spin, their color charge, entanglement, this single quantum idea shows up in so many different ways. It's incredibly diverse.
It really is. And this diversity, as we've seen, it's not just some, scientific footnote.
Right.
The fundamental nature of each particle, its mass, charge, spin, how it interacts, that directly dictates what properties you can entangle, how you entangle them, and ultimately what that entanglement is good for technologically.
It all connects back to the particle itself.
It does. The particle dictates the possibilities for harnessing that spooky action.
So here's a final thought for you to consider. If each particle type brings its own unique strengths to the table for entanglement, how might we get really creative? Could we harness these different strengths, maybe combine different types of entangled particles in new hybrid quantum systems?
Interesting.
Could that mixing and matching pave the way for completely new quantum technologies, things we maybe haven't even properly imagined yet?